All right, thank you, and hello everybody. Today I will present a little bit about OpenFOAM. I was supposed to present capabilities, application, and future direction. I don't think I will have time for future direction, so I will mainly give an idea of what OpenFOAM is, for those of you who don't know it, what has been done with OpenFOAM, what you can do. I kept it as informative as possible without dwelling too much into details. First of all, for those of you who don't know OpenFOAM, officially it is described as an open source CFD toolbox. It has capabilities that mirror those of commercial CFD. It's free to use. It's quality assured because the company that develops it is QA certified. And it's open source with the continuous poking from 20,000 more or less engineers since 20 years. So you can understand that there's pretty high quality. You look at the source code; it's very well written. There's a lot of issues that have been solved, thousands, and that to me is a sign of quality of a code. There's a lot of solvers if you want to do anything that is fluid dynamics. There's in there everything you want. Relevant for fusion, incompressible, compressible, multi-phase, particle tracking, can do molecular dynamics, Monte Carlo simulations, electromagnetics, and stress analysis, or finance if you want. All these solvers are available in OpenFOAM. Plus, since the community is vast, there's a lot you can find out there, packages that have been created on top of OpenFOAM that can be useful. I think a good example is Solids for Foam. It has been developed for many years at the University of Dublin. It has full capabilities for nonlinear mechanics. Now, OpenFOAM stands for Open Field Operation and Manipulation. This tells you that it's not just a collection of solvers, it's a large, well-organized HPC scalable C++ library. Aimed mainly at finite volume discretization, but it has a lot of functionalities. It has an object-oriented layered API. I say a lot of functionalities, of course, finite volume discretization. OpenFOAM is mainly a finite volume tool. It also has finite area method, arbitrary mesh interfaces, mesh-to-mesh projection, dynamic meshes, ODE solvers, Monte Carlo solvers, Lagrangian. It's a big library. It's like probably more than a million lines of code. So each time in the past I had to find the functionality that I needed, I found it in the mesh, in the code. And once again, community is vast, which means you will find additional functionalities created by the community. It goes from naval engineering to proper orthogonal decomposition. So you find a lot if you need to do very specialized research. What about nuclear? What did we do in nuclear? So I'm talking about nuclear because this has been most of my background in the past, but I think it's relevant for fusion in several ways. I'll be quick because this is not the main scope of today's talk. But essentially, OpenFOAM has been used in nuclear almost since the beginnings of OpenFOAM. So since I think OpenFOAM was released in the early 2000s, late 90s, and from the early 2000s it has been used during the PBMR project in South Africa. It has gained traction between 2010 and 2015, especially because there was interest in advanced reactors and we needed tools that were more flexible than legacy nuclear fission tools. Starting 2015, you start seeing some coordinating persistent developments. There are three I'm familiar with. One is GenFOAM, one is offbit, one is containment foam. First one is for multiphysics. Second one is for field behavior, or in general, non-linear mechanics with effective irradiation, which could be relevant in fusion for anything like behavior of materials in blankets, for instance, and containment studies. Now, without going into the details of all these tools, what is relevant is that from the nuclear community, there have been contributions that are useful for fusion. First of all, 1- and 2-phase flow in porous media with advanced capabilities, which can, of course, be useful if you want to simulate things like pebble bed blankets, or in general complex blankets, where it's hard to use standard CFD. We may want to, homogenize structure into something simpler and use correlation. That is available now. There's neutron diffusion and transport. There's a lot of work that's been done with coupling with Monte Carlo codes. First of all, how to do it, and some implementation. A relevant one is, even though it's not open source, is Serpent, in the sense that in the Serpent Monte Carlo code, the multiphysics interface, the native format for the mesh is an OpenFOAM mesh. So if you're doing OpenFOAM calculations, it's pretty straightforward to use your mesh in a Monte Carlo simulation. Read temperatures and density cell by cell and write to mesh everything you want, from power to tritium production. And the last piece is capabilities for nonlinear structural mechanics. This is what I was mentioning before. It includes effective radiation damage. It can be used to simulate stresses in components subject to neutron fluence, including things like irradiation and temperature creep, swelling, growth, embrittlement, change of properties, and so on and so forth. Still about capabilities, there's quite a bit of coupling capabilities in OpenFOAM. First of all, what I mentioned, Monte Carlo, there's an available interface in Serpent. In general, the coupling is pretty easy. Somehow, finite volumes and Monte Carlo have a similar philosophy. Finite volumes do balances in cells, and Monte Carlo scores tallies in cells, so the coupling is pretty straightforward. It's even more straightforward with delta tracking-based tools like Serpent. I believe that's the reason it was the first one trying to do this coupling with OpenFOAM. It's straightforward because pretty much what you do with delta tracking, each time you go, your neutron land in a place, the question is, where am I? And OpenFOAM finite volume can give a fairly rapid and straightforward answer using an octree algorithm, search algorithm for the mesh. There's coupling with ODE-based tools. It's available through the FMI. For those of you who don't know FMI, FMI stands for Functional Mockup Interface. It's a coupling standard that has been proposed more than 10 years ago, I think mainly in the automotive and aeronautic industry. The idea is relatively simple. Instead of creating dedicated code-to-code coupling for every couple of codes, the idea is we create a standard. If you abide by the standard, you will be able to couple yourself with any other tool that abide with the same standard. It's pretty powerful. FMI is already implemented in, I think, 170 modeling tools out there. That includes things like MATLAB, Simulink, and Modelica, but also ANSYS, and several other tools. And the German Aerospace Center has developed a FMI capability for OpenFOAM, which means now you can, for instance, couple fairly straightforward OpenFOAM with Simulink or Modelica or any other, for instance, system level tool. Similar, but for PDE, some of you may know it, there's a coupling interface that has been created, once again, in Germany. It's called Precise. It allows coupling of several PDE tools, and one of the tools for which there's an interface available is OpenFOAM. So through Precise, you should be able to couple OpenFOAM with several other tools, and in there's a lot of finite element libraries. I mean, in the tools that are supported by Precise. And if your tool is not there, Precise developer promised that it's pretty easy to develop an interface for your own tool. The philosophy of Precise is very similar to FMI. It's as long as you do things as we tell you, you will be able to couple yourself with any other tool. Important thing is for OpenFOAM, there's already a Precise interface and an FMI interface. Now, more specifically about Fusion. So what I did is I Googled, actually on Scholar, OpenFOAM Fusion. and turns out that there are tens of articles. What I did is I extracted a few that I believe can give an idea of what people are doing with OpenFOAM, plus at the end a couple of slides of work I've been doing. MHD, of course, you can do that. Interesting, you can do MHD with free surface, which is not an obvious capability. There's a lot of MHD capabilities for internal flow, but free surface flow, it means you can do two-phase flow and MHD. There was actually MHD in multi-phase. I actually did it for a bubble rising. Once again, pretty unique capability. There have been students actually that have tried to develop a diverter, box type, with two different methods, from Euler-Euler two-phase, very standard two-phase flow, to very complex and potentially higher fidelity direct simulation Monte Carlo. I compared the results, and well, it was a master thesis, but it was complete enough, an interesting piece of work. I found work on beryllium melt motion and splashing from first wall in ITER. And of course, there's an example that has to be mentioned. There's a fairly large project at ORNL. It's called Fermi. And within Fermi, well, Fermi actually uses the precise coupling interface that I mentioned before, together with OpenFOAM and a few other tools. And it's a relatively large effort, and a big part of it is on OpenFOAM. So there are, you can find, if you Google the work from Oak Ridge, you will find several simulations of related mainly to the arc concept. This is an example from work I've been contributed to. And this work, OpenFOAM, was used to simulate the transport of nitrogen-16 in ITER. It's a relevant piece of work in the sense that ITER has experienced some delays because of nitrogen-16. It's turned out that a big piece of radiation to the public may come from nitrogen-16, so it was very important to understand how much nitrogen-16 was outside of the core pretty much. And to do that, something you can do is you use OpenFOAM, you use standard CFD, you add on top a scalar transport. You create a source term using, for instance, MCNP. You transport with OpenFOAM, you do the CFD, and from the vacuum chamber, from the cooling of the vacuum chamber, you connect it with a system level tool, and you try to figure out where nitrogen-16 is everywhere in the system. And the last piece of work, it's actually related to inertial fusion energy, something that we discuss much less, but this is gaining traction. The chamber of inertial fusion energy is a big engineering challenge. Well, it's not like achieving fusion is easy, but sometimes, you know, there's a tendency to think that that's the only problem. Actually, there's another problem, is how do you design the chamber to extract energy? And the process is pretty complex because once fusion happens, you have to protect your walls. One way to do it is to use liquid walls. If you do that, the X-rays from fusion will ablate part of your liquid. Ablation will create a shock. Shock will propagate through the chamber towards the interior and then outside, and it will create loads on the wall, splashing of the jets. You will have to clear the chamber. So you need the tool that is able to do jet breakup, shock dynamics, radiativity transfer sometimes if needed, and OpenFOAM has all these capabilities. And I think I'm getting very close to the end of my presentation. Do I still have a few minutes? Or is better if I leave for
questions? You're at like 14 and a half minutes, so kind of roughly tied up if you can. I can.
I'm actually done. If I had more time, I would give some future direction, but it's I was essentially done.
Feel free.
Oh yeah, something maybe I wanted to mention about future direction. So I mentioned briefly this tool, GenFOAM. I mentioned Offbit. These tools provide, put together, you can do pretty much everything from, shock dynamics to fluid dynamics to structural mechanics. And currently these tools have been integrated into a single tool so that you don't have to do coupling yourself. You can directly use both. This can be used to do, for instance, if you want to simulate a blanket, you can do both the fluids and the structural mechanics in the same environment. It's work that still needs to be published, but it's already available because both of these tools are available on GitLab for free, just open access. And if you look at GenFOAM, you will find that it already includes capabilities of Offbit. And we are working on introducing some Fusion relevant tutorials because for now it's mostly fission. And that's it.
All right, brilliant. Thank you very much, Carlo. Yeah, OpenFOAM is something that actually we've been trying to figure out a bit ourselves, see how we can couple it with our own code. And some fantastic examples there. It's clearly a very powerful code and amazing that it's open source. So I have a question for you already. Sure. I have a nuanced relationship with OpenFOAM. It's always been very attractive from a feature standpoint, but somewhat repulsive from a user-friendliness point of view. Are there any plans to make OpenFOAM more user-friendly, a Python API, a GUI, or something else?
Not on my end. I mean, I can tell you that the community has been trying to develop GUI for a long time. There are some out there, some you have to pay for, some free. What happens is that most of OpenFOAM users in the end don't use that. The thing is, with OpenFOAM, you have a very steep first entry barrier. But once you get used to it, it's addictive somehow, or it's kind of easier to use compared to using a graphical user interface. I think that to me the more challenging part is, well, the first entry barrier and the fact that there is no native meshing tool. That is more of a pain, but OpenFOAM allows you to use pretty much any tool out there, from Salome to Qubit to ANSYS, and convert meshes to OpenFOAM. But no, as far as I know, there are no free-to-use, very commonly used graphical user interfaces, and I'm not aware of any plans to create them. And the plans that have been tried in the past, as far as I know, they didn't succeed, or not as much as they expected to. Did I answer your question?
Yes. And another question from Jake. What neutronics tool did GenFOAM use?
GenFOAM has diffusion, SP3, and discrete ordinates. Now, diffusion and SP3 might be questionable to use in Fusion. Discrete ordinates you should be able to use. It's not honestly the best implementation available. It's pretty slow, but it works. And something we're working on at A&M is coupling OpenFOAM with OpenSN. OpenSN is a very powerful, very fast discrete ordinate tool. It's also open source, by the way. And we are trying at least to create an external coupling so that you can read an OpenFOAM mesh, temperatures and densities, and write back to OpenFOAM information like power distribution.